Okay, let's get started. So, welcome back to Introduction to Photonics. We've been talking about semiconductor light sources, and in the last lecture we were talking about characteristics of semiconductor light emitting diodes, and we were essentially looking at the emission characteristics, the output power as a function of injected current, and then the modulation characteristics, as well as the spectral characteristics. Today what I would like to do is extend this discussion to semiconductor lasers, and semiconductor lasers are not very different. It's not such a new topic, because even while we are talking about semiconductor light emitting diodes, we said if you had feedback from either ends of your this double heterostructure, you will end up having a laser emission. And so in some ways, like I said, semiconductor lasers are easier to do than LEDs. LEDs are going to have to go through this extra step of doing some surface treatment, especially at either ends of the active region, such that it frustrates total internal reflection and you could get light out of the structure, right. So, for the laser you do not have to do anything, you just have to take a double heterostructure and cleave on either side of it, and you just based on that reflection you will build a laser. So, what we will do today is consider some of the characteristics of semiconductor lasers, and to help our discussion I just picked one of the problems that we have in the present tutorial. So, this is asking you to consider a indium gallium arsenide semiconductor laser. The material refractive index is 3.7. So, this is emitting at 1.3 micron wavelength. So, you can imagine that the band gap energy for this material has corresponds to a wavelength around 1.3 microns, and so it consists of a 0.4 mm long cavity, that is basically 400 micron long cavity with internal losses of 40 inverse centimeter and mirror reflectivity of 0.9 at either end. So, the mirrors also contribute to the losses, the overall cavity losses. So, find the frequency spacing between the longitudinal modes of the laser. So, that should be relatively easy to do. We know that it is corresponding to C over 2 and L. So, N is given, L is given, so it is just a direct substitution. Find the maximum gain required to compensate the losses in the laser cavity. So, that part we will look into little more detail, and finally derive an expression for power emitted from the laser in terms of applied current. Applied current, the losses, and eta int. Okay. So, we'll try to find such an expression as well. Okay. So, and then of course if you assume eta int is 1 and the threshold current is 50 milliamps, find the optical power emitted at 100 milliamps of drive current. Okay. So, let us say this is what we want to achieve. So, let us just go into the specific structure of a semiconductor diode laser. To understand that, let us just first of all define the double heterostructure once again. So, we said we are going to have a double heterostructure consisting of a P region and an N region. right, and an active layer in between, which corresponds to a material with lower band gap energy, so that it accumulates all the carriers. And if I were to just project this in 3 dimensions, so just give you a perspective of this, it is going to be something like this. And in order to have a current injected, so what you normally do is you have a layer here, a contact layer, right, and then you define a stripe in the top region as well. So, that is basically a metallic contact to which you can connect an external source. So, you can imagine that the current that is flowing through this structure is going to be something like this, right. So, all the carriers injected are going to be around the center of this facet. So, when you look at the light that comes out of this laser, you can say that it is going to come out of this region here, okay. And one characteristic that we can clearly see is it is limited by the thickness of the active region, right, in the vertical direction. So, that is basically how many layers you can deposit in epitaxially, and in the transverse region or the horizontal direction, there is not as much of a constraint. So, the vertical thickness could be in the order of a micron, but in the horizontal side there is not as much of a constraint. So, when you look at the light that is emitted from this structure, what you tend to see is that the light that is emitted in the vertical direction, since it is coming from a smaller aperture, it tends to diverge much more, right. So, whereas if you consider the light that is coming from the horizontal direction, that does not diverge as much. So, because it is coming from a larger aperture. So, larger the aperture, less will be the divergence, right, and if the aperture goes down to a dimension comparable to the wavelength, then you would have much more it is basically diffraction effects come into the picture. So, you will have much more divergence from that region. So, effectively your output beam is going to look something like this. So, on the horizontal direction it will not have much divergence, but the vertical direction it will have much more divergence. So, this is actually something called astigmatism. If you go to an eye checkup, so your ophthalmologist may tell you that you have some astigmatism. So, what does that mean? It means that your curvature of the lens in your eye is actually not the same in both directions. So, you would have to have some special type of lens with different curvatures on either direction to correct for that. So, similarly we have an astigmatic beam, and to correct for that, what you need is actually what is called a anamorphic lens, right. So, it needs to, it's basically a lens with two different focal distances for the two different directions. and with an anamorphic lens you can essentially correct for this astigmatism and possibly get it to a circular beam. Why do we need a circular beam? Why is that we might need a circular beam? We talked about coupling into an optical fiber eventually. So, it's basically got a circular cross section. So, you need to fit this beam into that optical fiber. So, you may want to have a circular beam, right. So, that is one property of all edge emitting sources that you typically have astigmatic light output, and you may need to correct for that astigmatism before coupling into the optical fiber. But anyway, coming back to answering this question, we first of all need to understand what is the gain that we are able to achieve as a function of the injection current. So let us try to look into that, and let us first try to look at the gain as a function of injection current for different energy of light that is emitted. Okay. So, if you are looking at the gain coefficient, which is expressed in inverse centimeter, right. So, if you look at the gain coefficient as a function of h nu, we can tell that there is nothing that is going to happen for energy less than band gap energy. Why is that? No energy levels exist, these are all forbidden. So, you are not going to have any action happening to the left side of Eg. So, initially if you are not injecting any current into this structure, okay, and if you are if you are sending light in, basically it will act like an absorbing medium, right, because you have all your electrons in the valence band, no electrons in the conduction band. So, now when you have light with energy greater than h nu, what you are going to have is all absorption, right. So, higher energy, higher frequency have more absorption because more density of states exists. So, you can have higher absorption over there, but the absorption starts at Eg, right. So, this is if you do not inject any current. Now, you start injecting some current, then you can start having gain, right. And so, you will start having this sort of a picture. And so on. And what you will see in general, so this is as a function of increasing current injected, and what you see is that the peak gain value is increasing, and it is also shifting to higher frequency. Why is that? Why do you have more gain when you have more injection current at higher frequency? Because initially when you inject current, you are filling the lower energy levels of the conduction band, right. And so, you start emitting from those levels. So, the energy of those emitted photons are going to be lesser. So, let me just try to draw that over here. So, if this is my conduction band, this is my valence band. and then you have much higher density of states. So, similarly low density of states and then much higher density of states over here. So, initially when you inject some current, you are having electrons over here and holes over here. So, you have this recombination happening. So, that energy is low, but as you start injecting more and more electrons and you have more and more holes in this valence band, you start having deeper and deeper emission, right. So, you are emitting from a deeper level in the conduction band to a deeper level in the valence band, and as a result of which the gain, the peak gain happens at a higher energy level. Okay. Do you understand that? Any questions about this before we move on? Okay. So, now let us track here the peak gain in inverse centimeter. Just one second. As a function of the electron density, there is a question there. That is right. So, the question is Fermi direct distribution tells you that lower the energy level, more is the probability of finding an electron. That is absolutely true. But there is also Pauli's exclusion principle, which says that if I fill my lower energy levels, I need to keep going up. So, I cannot have more and more electrons in the same state. So, the extra injected electrons are going to start occupying higher energy levels. So, typically, with emission, yes, typically you are saying that you will have emission from the lowest energy level. So, you have more emission near the band gap energy, right. That is what we typically say. But as you populate more and more electrons, the higher energy levels, you start having this possibility of the peak shifting to longer or higher energy levels, because you are starting to have more electrons in the deeper in the states, and then you would have these emission. Yeah. No, it can be. I mean, so that is the biggest difference between an atomic system and this semiconductor system. In the atomic system, you could have essentially different atoms in different places can have the electrons at the same energy level, right. So, you could have that happening across the matrix, but as far as semiconductor is concerned, you are going to, I mean, you are excluded from having, this is actually a combined system, right. It's a coupled system. So, you are excluded from having more than one electron at any state. So, you are actually having to, once you have filled it, you are having to go deeper, you are filling the deeper states, and then relatively you are saying the peak is shifting to, the peak gain is shifting to longer wavelengths, I mean higher energy transitions, which correspond to shorter wavelengths actually, because you have more states, the density of states is more, so more electron population there, and because of that you could have more gain for higher energy levels. Okay, it's a relative thing, but you're right that it tends to stick closer to the band gap energy, but yeah, as you pump harder, you can go away from the band gap energy. Any other questions? Okay. So, let us track this part, and what we said was that initially you do not have much electrons in the conduction band. So, your initial injection does not really give you much of a gain. So, initially what you have is just absorption, right, from the material. So, that is actually, so you can say this gamma p is 0 over here. So, you have a negative gain which is corresponding to a loss in the medium. And then as you increase, you get to a point which corresponds to NT, and this is actually called transparency. At transparency, you have a net gain, right. I mean, you have overcome the losses in the material. Okay, you have overcome the losses in the material, and you are starting to have a net gain beyond a certain level of electron density. And beyond that, you can increase like this. Okay. So, now comes this concept of when you make a laser, you have extra losses in your cavity, right. You could have this background losses in the cavity as well as your mirror losses in the cavity. So, that extra loss level may be somewhere over here, alpha r, right. And that means until you get to a value NTH, which corresponds to a threshold, only beyond that you are having, I mean, you're starting to have lasing happening. Okay. So, you are essentially having one point where you are overcoming the absorption in the material, you are starting to have a net positive gain, but you need to have more gain beyond that to overcome the losses in the cavity, and then only you can have laser emission. Yeah, you have a question. Background losses as in scattering type of losses you may have in the material, or you can have impurities in the medium which are giving rise to some background, if you have some, I mean, in glasses it is common to have some metallic impurities and some contamination, and those could cause background losses. So, that's the extraneous losses that we are talking about. So, N is the electron density. So, the electron density in the conduction band, right. So, that effectively you are tracking that, because those are the ones that are going to give you potentially this recombination and give you stimulated emission or gain. Okay. So, you have two different quantities that you are having to track, and let us say you are having alpha corresponding to the loss in the medium, then you can write your peak gain coefficient as gamma p is going to be equal to alpha multiplied by n over nt minus 1, right. So, that represents this straight line over here. Let us just quickly check. When n equal to 0, gamma p is equal to minus alpha, right. So, this is basically you are saying it's negative gain, so which is corresponding to minus alpha, and when n equal to nt, that is the transparency density, then gamma p equal to 0, right. So, that is just a quick check to see that this indeed correspond to equation of that line. And we know that the electron density is going to be corresponding to the current that is injected, or in other words the current density. So, you can write this as J over Jt, where J corresponds to the injected current density. Jt is a constant for a given material corresponding to the current density required to achieve transparency. That's a net gain of 0. Okay. So that is the expression for your gamma p, right. Now, what happens at threshold? At threshold, we are saying that gamma p has to be equal to alpha r, the gain has to be equal to the loss, right. And this loss we are saying, but gamma p is also given by alpha j, but we are considering a threshold condition. So, we can write this as j threshold divided by jt minus 1. Okay. So, gamma p from that expression at threshold j equal to j threshold. So, alpha into j threshold over jt minus 1 correspond to gamma p, or you can write that if you are trying to find the threshold current density, that threshold current density, if you just rearrange these terms, you are going to find that that's going to equal to alpha r plus alpha divided by alpha multiplied by jt. So, the threshold current density is greater than or equal to the transparency current density, because you are needing to have extra current injected to overcome the losses in the cavity, right. So, and that how much extra is determined by this factor alpha r over alpha. What is the resonator losses compared to the the loss in the material itself, the absorption in the material. Okay. Any questions about this? So, we are generally saying the threshold current density will be greater than the transparency current density. But you understand this picture? Any issues with that? Gain as a function of electron density. Okay. Let's move on. Yes. When the? Oh yes, so the question is whether there will be saturation of the gain. Yes, I mean as you emit, your electrons are getting depleted from this conduction energy levels, and even if they deplete from the bottom, they are actually going to trickle down to the lowermost energy level. That is what the other question was about, and corresponding to that, you will have lesser gain for the longer energy transitions. So, for the shorter wavelengths, you are going to have lesser gain, and in general, yes, there is a gain saturation effect. All those things that we talked about in terms of gain saturation is valid for this also, except that there we talked about some emission cross section, and the saturation time. So, those definitions change here. So, there is still a saturation time here as well. yeah, but the definition of the emission cross section and all that changes. Okay. So, let us move on now. What we want to do is quantify these things. Now, right here I can say that C over 2 NL, so delta nu is going to be equal to C over 2 NL. So, C is given as 3, well C is we know 3 to 10 power 8 divided by 2 multiplied by 3.7 multiplied by L, which is 0.4 mm. So, 0.4 into 10 power minus 3. So, what is it? 0.8. So, that is about 3. So, 3 and 3 cancel. So, it is roughly about 10 power 11 hertz. That is corresponding to 100 gigahertz, right? Huh? 9.375. So, 93.75 gigahertz is the accurate answer. I was just giving some rough numbers, but this is 93.75 gigahertz, right? That's, huh? It has to be in gigahertz, 10 power 8 divided by 10 power minus 3. Huh? What's the number you are giving? You are giving some other number, okay. 1.01. Oh, that's more like it. That, yeah, that is 10 power, that's 100 gigahertz, 101 gigahertz, okay, yes, okay, that's more like it. I thought I couldn't be that wrong. Anyway, so that is straightforward. So, we are saying that we are going to have one mode, so if we were to represent that in the same picture over here, you have all these longitudinal modes here, and those longitudinal modes correspond to 100 gigahertz, right? And then the second part is, what is the minimum gain required to compensate the losses in the laser cavity. So, that part, if we were to write it out, so just like what we did before, your gain has to be equal to alpha int plus 1 over 2L ln of 1 over R1 plus 1 over 2L ln of 1 over R2, and in this case R1 equal to R2. So, I can actually say overall it is 1 over L into ln of 1 over R. That is reflectivity is given as 0.9. So, you can plug that in and you can find that answer. So, this is 40 inverse centimeters, and the other one is 1 over L corresponds to 2.5. So, that would be roughly about 42.5 inverse centimeters, right. So, you can do the math and you can verify that. Okay. Now, let us go ahead and try to derive an expression for the power emitted from the laser. Okay. So, let us try to do that part. For calculating the power emitted, you will have to look at first of all the internal photon flux. Let us call it phi in, and that is going to be given by eta I, just like we did for the LED case. It is going to be given by the internal quantum efficiency which depends on the radiative rate over the total radiative plus non-radiative rate. And then you are going to have emission only for current beyond the threshold current. So, I minus I threshold over E, and that is what you have for I greater than I threshold. It is approximately 0, it is not really 0 because there is still spontaneous emission, but you can approximate that to be 0 for I less than or equal to I threshold. Okay. And if that is the case, then you can say that the output photon flux phi out, that is got to be some factor of the input photon flux. What is that factor? We are calling that eta E times phi in, where eta E corresponds to, if you are looking at the power coming out of mirror R, mirror 2, then that is alpha M2 divided by alpha R, right. So, that will be the fraction of power that you are extracting from the cavity, right. And from photon flux, hopefully by now you know how to write the expression for output power P out, that just what? Phi out and then times h nu, the energy of the photon, right. So, if you were to write it all out, we would say this is equal to eta I, eta E, I minus I threshold divided by E multiplied by h nu. So, you can track this, right, just like we did previously. The only thing that has changed is with respect to the LED, only this factor has changed. Before we were just saying I over E, the rate at which we were injecting current. So, not all that injected current gives rise to laser emission. You have to overcome threshold, and beyond that whatever injected current you have gets converted into photons with energy h nu, and the internal conversion efficiency, and then the external photon, photons that we get coming out of the cavity. Okay. So, typically just like what we have seen before, output of a semiconductor laser as a function of the current injected, you have something called a I threshold. Up to that it is only spontaneous emission, and then beyond that you could have stimulated emission, and you could get output power. So, you can, so where all these lasers used for a variety of applications, starting from UV lasers. UV lasers could be useful for lithography applications, right. Shorter the wavelength, less will be the spot size that you can get, because the diffraction limit, right, that scales as a function of wavelength. So, shorter the wavelength, you can get smaller feature sizes. So, if you want to do lithography with very small features, you use ultraviolet light sources, and lasers can be used for that. Ultraviolet lasers are also packing a lot of energy. Each photon now is got several eV of energy, right. So, so ultraviolet lasers could also be used for ablating materials. So, you can actually break bonds of several materials with UV radiation. So, use UV lasers, and then you go on to blue and green type of lasers. This blue lasers are what is used in your Blu-ray discs, right, in your DVDs and Blu-ray discs and all that. You use shorter wavelengths specifically for that reason, that you need to have very small features detected. Okay, and then you go on to green lasers. You have these red lasers. The red laser pointer is something that you have seen a lot. A green laser is also another thing that you have seen. Although when you talk about a green laser pointer, we are talking about slightly different concept. I think I touched upon briefly. There is something called second harmonic generation going on. So, that laser is actually a 1064 nanometer laser, but then if you do a nonlinear conversion, which we will talk about later in this course, if you are able to do that nonlinear conversion, you can convert 1064 to 532 nanometer photons, which is used in the green pointer. Okay. So, and then of course, you go on to using 800 nanometer laser diodes, 980 nanometer laser diodes. Where is 980 useful? Pump diodes for your amplifiers. You know, we saw with your erbium or even ytterbium also has gain around 980 nanometers. So, you can use these lasers to pump other lasers. Okay. And then so on, then 1.3 micron, 1.5 micron, these are all useful for communication applications. And now people are looking at going into the mid-infrared. So, I was talking about sensing applications. You need light sources in the 3 to 5 micron wavelength band, and people are looking at making sources there. So, in all of this, what matters is, you know, if you want to get a particular energy photon, you choose a material or you engineer a material. So, that is the beauty of semiconductors, as opposed to these atomic systems where all your energy levels are all pre-chosen by God. Right. So, you cannot do anything about those energy levels. You just have to work with whatever you got. With semiconductors, by changing the material concentrations and mixing different material, you can get band gap energies over a wide range, right. So, you can achieve lasers over a wide range of wavelengths with semiconductors, right. So, you choose the corresponding band gap energy and then you achieve lasing at that particular wavelength. So, let us see. So, that is one thing I wanted to mention, and also these are fairly efficient because the slope efficiency of this can be in the order of 50%. So, and the threshold currents can be in the order of 10 milliamps or so. So, effectively with no current, with negligible amount of current, you are able to achieve threshold, and beyond that you are converting your current into light energy. So, overall you can say that the wall plug efficiency of these lasers are in the order of 50%, which is very, very high, because if you talk about this traditional gas lasers and dye lasers and all of that, the wall plug efficiency is fraction of a percent. Even the solid state lasers that we have, the bulk crystal based lasers, the wall plug efficiency is only in the order of 5 to 10%, but this can give you much better wall plug efficiency. Essentially for unit electrical power, how much optical power are you generating? So this can give you some of the best numbers that you can see as far as wall plug efficiency is concerned. But in terms of power that you get out, these tend to be in the order of 10, 20 milliwatts, around tens of milliwatts levels for single mode diode lasers, because you cannot inject beyond a certain current level into it, because once again, like we talked about in the case of LED, if you have very high current density, then you have collision between the carriers and that generates heat. There is something called O'Shea recombination that happens, and because of that the overall efficiency starts taking a dive. So, you are limited in terms of the power levels. On the other hand, I should also mention that in our laboratory we have lasers that emit 120 watts is the highest power level that we have from a semiconductor laser. So, here I am talking about tens of milliwatts, there I am talking about tens of watts. So, what's the difference? First of all, the semiconductor lasers that we have in the lab, they are all multi-mode lasers. So, multi-mode, what are called broad stripe lasers. So, you have a fairly large region over which this emission happens, the stripe over, so it is a fairly broad aperture over which this emission happens. So, as you increase the gain volume, right, as you increase the gain volume, you are able to generate, you are able to tolerate much more injected current, and you are able to generate much higher power levels. But what gives in this? Can you guess? As you increase your aperture size, it starts becoming much more than your size of your wavelength. So, what do you have if you have much larger size? Well, this is basically what I have written here. These are a multi-mode. So, your spatial coherence reduces. You have multiple modes that are oscillating. So, you have very low spatial coherence. So, the lasers that we use, they are all multi-mode lasers. They are actually coupled into a multi-mode fiber. So, what I am getting is each laser is about giving about 10 watts of power, okay, and I have multiple lasers that are stacked on top of each other, and overall the emission, it starts looking like one large beam. So, you can use some optics to shape the beam and then couple it into a multi-mode optical fiber. So, the fiber, the laser that I have has 12 emitters, each one of them emitting 10 watts of power. I should also mention that I am getting 10 watts of power with just a little bit over 10 amps of current, okay, and so this is basically roughly about 11 amps of current, and you have basically 2 volts is the typical voltage drop across any of these diodes, right. So, roughly about 22 watts. So, for 22 watts I am getting 10 watts of output power, 22 watts of electrical power I am getting 10 watts of output power. So, that is pretty good, right. It's close to 50% wall plug efficiency. So, all of this combined is giving me 120 watts in a multimode fiber, which is 105 microns in core diameter, 125 microns in cladding diameter. Okay. So, I can have multiple emitters to scale up my output power, but with a single emitter, with a broad stripe emitter and all that, you are not going to be able to go much beyond 10 watts of power. So, right now people are stacking more and more elements. The other day the record that I was seeing is about 350 watts of power from a very compact package. I mean, a package the size of your mobile phone, you can get 350 watts of power. And that, of course, you know, when you say 50% slope efficiency, 50% wall plug efficiency, where do you think the other 50% goes? It's generating heat. Okay. So, if I am generating 120 watts of optical power, I am generating 120 watts of heat also. So, now I need to have these cooling plates and all that. So, these lasers are typically mounted on cold plates, where we circulate cold water and all that. So, we can keep the temperature, the operating temperature is still in the order of 25 to 30 degrees centigrade. So, that is important. So, as you scale with higher power levels, you need to have more and more efficient dissipation of heat that is required. So, that eventually determines what is the size of your laser diode also, right. So, you are not going to be able to keep it very compact, because you need certain volume to dissipate your heat. Okay. So, did I answer all these questions? Well, the last part, assuming eta int equal to 1, I threshold 50 milliamps, find the optical power emitted at 100 milliamps. I suppose that is once again just substituting into these those corresponding values, and then you get the output power. Okay. So, the only thing you have to calculate is eta E, which you can calculate as alpha m2 over alpha r, then you get the output power. So, let me stop at that point. The spectral characteristics, once again we talked about multiple longitudinal modes. It is homogeneously broadened. So, normally you expect only a single mode to be oscillating, but in reality there is actually, because of spatial hole burning, the the longitudinal modes where it oscillates, it is jumping around. So, the average spectrum looks like a bunch of longitudinal modes oscillating together. But one thing maybe I will mention is there is a specific class of laser known as DFB laser, wherein if this is my active medium, I am just this is my active layer. If I put some perturbation along this, and let us say my perturbation is such that this capital lambda, the period of that perturbation provides reflectivity at a particular wavelength called the Bragg wavelength. Bragg wavelength is given by 2 times n effective times capital lambda. Okay. Then that particular wavelength is going to be reflected all along the length of the cavity. So, this is called a distributed feedback laser, or in short it is called a DFB laser, right. A DFB laser operates at a particular wavelength, only at this wavelength, just like the experiment you did. You put an external grating right? Well, external in the sense that it is not part of the gain medium, it is outside the gain medium, but it is all part of the cavity, and you are able to show laser oscillation at only at a particular wavelength. So, similarly, if you have distributed feedback laser, you can actually get single longitudinal mode operation. Okay. So, with a distributed feedback laser, you can actually have only one longitudinal mode oscillating. So, sometimes it is loosely called as a single frequency laser also. Okay. Although there is no such thing as a single frequency laser, even if it is operating single longitudinal mode, because of the phase noise associated, it will actually have a finite spectral width in the order of megahertz. Okay. But you can get some special properties with these type of lasers, which is just an extension of a regular Fabry-Perot cavity. Everything else is the same, except that you have put this grating over that active region. So, it provides feedback only for one wavelength. Okay, every other wavelength it's feeling loss. Okay, any questions before we close? Sorry? No, it does. So, in this case you do not need any mirrors, because these provide all the feedback you want. So, in fact, you may want to frustrate other modes from oscillating. So, you may want to actually put anti-reflection coating on either ends. Okay. The feedback is provided just by the grating itself. These are the slope efficiencies, the numbers that I am quoting, these are all typical laser diodes that you get, right. So, this is not some exotic laser, and this one, like I said, to get 10 watts you are pumping in only 11 amps, that is something everybody can make these days, right. So, that is readily available. So, the efficiencies have I think the highest efficiency for a commercial device is about 65% efficiency. So, that just means that you start with a very good material, you have very little background losses, and so you are able to also give a structure where the conversion efficiency is very high. Yeah, so question is about VCSEL lasers. So VCSELs are essentially what we talked about yesterday, vertical surface emitting lasers. So yesterday we talking about surface emitting LEDs, but in this case what you do is you can actually put sort of a periodic layer over here and periodic layers, high and low refractive index layers over here. So, you are essentially having a Bragg grating here and a Bragg grating here, and you define your electrodes in sort of a ring fashion. So, the bottom electrode is like this. But if the top electrode, if I am looking from here, this will look like a ring electrode. So, your current injection is essentially happening across this entire region, right. So, you once again have in this case you have an active layer here where all the recombination is happening, and then it is actually reflected by this top mirror and the bottom mirror. So, the laser emission actually happens in this direction. So, you have light emission happening over here. So, this is called a vertical cavity surface emitting laser, VCSEL. Okay. So, VCSELs like I said yesterday, the beam quality is defined by the ring structure. So, you can actually get a nice circular beam as opposed to the astigmatic beam that you are getting from edge emitting lasers. With VCSELs, you get light circular beams. So, that actually means that you can couple it easily into an optical fiber, typically a multimode fiber, because unless you define the ring structure to be very, very small, so that light emission can be single moded. But you get very nice circular beams out of these VCSELs, right. So, those are good for certain applications. That is the electrode, yeah, that is the top electrode, and then you have the bottom electrode, which is totally planar. Huh? No, the bottom electrode can be continuous. Top electrode, a ring only to define an aperture through which light can escape. Yeah. So, that is an important point, yes. So, you have to have a material that is not like a very good conductor, it's still you have to have different refractive index and all that. So, you compromise that a little bit, but in general, yes, it shouldn't give you a lot of loss to the, it shouldn't give a very high resistance to the current that is going through. Okay, so let us stop here and then come back. We will meet again tomorrow to discuss semiconductor light detectors.